Welcome back to our very last topic for this chapter, section 912 on percent yield. I'll give you a few seconds to copy down your notes. Okay, so our very last calculation we're going to learn how to do is percent yield. And this is important because we have been calculating theoretical yields. When we do these stoichiometry problems, we are calculating what you should get in theory. So this is the maximum amount of product that could be created from a given amount of reactant in grams. In all actuality, though, you are not going to end up with that much product. This is for many reasons, a few of which, one reason is that there are side reactions that go on. There are other reactions that are going on than the one that we are looking at. For instance, perhaps what you're working with is also reacting with oxygen in the air. Or perhaps some of the reactants are sticking to the side of the beaker, your glassware. Or maybe you just can't scrape out all of the product at the end, so you lose some there. So these are all things that can happen. So something that's useful to calculate, especially in industry, is percent yield. This is the percentage of the theoretical yield that was actually produced. This is an important indicator of efficiency for chemical manufacturing companies. Companies want to know, how efficient is this reaction? How much money am I losing? How much money am I making? It's all about money in industry, so this is important for that. And the equation that we're going to use is actual yield over theoretical yield times 100%. So let's take a look at a problem. I will give you a couple of seconds to stop your video to copy this down. Okay. So our problem is aluminum hydroxide is found in many antacid tablets because it reacts with hydrochloric acid from the stomach to form aluminum chloride and water. So the first thing we need is a balanced equation. So this is a lot of review here. So we have to get a formula from aluminum hydroxide first. So we know for this that we have aluminum, we have hydroxide. Now, we can't just write it that way. We have to go back and we have to look at our oxidation numbers. Aluminum has an oxidation number of +3. Hydroxide, that's a polyatomic, so we have to go to our table E, is right here, charge of -1. So remember, crisscross. So we rewrite this as AlOH3, putting the parentheses around hydroxide because that acts as one particle, one unit, plus hydrochloric acid, which if we go to our acids chart, right here, some common acid, hydrochloric acid, HCl. Yields. So it reacts with hydrochloric acid to form aluminum chloride. So Al3 positive, chloride, we go to our periodic table, chlorine right here. The most common oxidation is -1. We're going to crisscross. So we get AlCl3 plus our water, H2O. And I'm not too concerned about the states of matter here. What I am concerned about is balancing. So what I'm going to look at first is, I really spot this chlorine here. 3 here, only 1 here. So I want to put a 3 out front. That gives me 3 hydrogens and 2 over here, but I also have 3. So I have 3 plus 3 is 6, so I want to put a 3 here, and that also gives me my 3 oxygens. So this looks balanced now by putting those 3's in front of the hydrochloric acid in the water. So now I can go ahead and work on a problem. So if 15 grams of aluminum hydroxide is found in a single tablet, determine the theoretical yield of aluminum chloride that would form if you assume there was an excess amount of hydrochloric acid. So I start out with my 15 grams of aluminum hydroxide. I cannot leave it this way. I have to convert to moles. We're going to make our molar mass sandwich. So I need to figure out the molar mass of aluminum hydroxide. So let's do that down here. So I have 1 aluminum with a mass, if I look that up on my periodic table, it's 26.98 grams. Now be careful here. I have 3 oxygens because this is in parentheses. So 3 times 16.00 grams from my periodic table. And I have 3 hydrogens, so 3 times 1.008 grams. If I do the multiplication and the addition, I get a total of 78.00 grams. So that goes on the bottom here. And that is 1 mole of aluminum hydroxide. Okay, now that I'm in moles, I can convert over to my aluminum chloride. Okay, because I'm looking for aluminum chloride. So, looking at my balanced equation, I have nothing out in front of this, so it's 1 mole of aluminum hydroxide. I have nothing in front of my aluminum chloride, so it's also 1 mole of aluminum chloride. Now I want to know the theoretical yield, and that is always in grams. Now I'm crossing out my units, making sure that the tops and bottoms cross out. 1 mole of aluminum chloride. So I have to go find my molar mass down here. Is aluminum, again, is 26.98 grams. My chlorine, I have 3 of those, so 3 times from my periodic table, 35.45 grams, for a grand total of 133.3 grams. So I put that up here. My moles cancel, and what I end up with is 25.63 grams of aluminum chloride. So that is my theoretical yield. Now notice my molar mass sandwich. Molar mass, mole ratio, molar mass. My meat is in the middle, and there's my breads on both sides. Now, I want to go a little further with this problem, and I want to ask if 23 grams of aluminum chloride were measured in the products, calculate the percent yield. So I'm after percent yield. So my formula is actual yield over theoretical yield times 100%. So I'm running out of room here, so I'm just going to do that over here. So 23.00 grams, because that's my actual, over my theoretical that I calculated up here, 25.63 grams times 100, and I get 89.74% for an answer. So let's go ahead and do problem number 2 on page 236 as one more example before you do your homework. So problem 2 says, in regard to the reaction introduced in question number 1, and that reaction is 4 moles of iron will react with 3 moles of oxygen to give 2 moles of iron oxide. So that is our reaction. If 200 grams of iron react fully with oxygen, what is the theoretical yield of iron oxide? So for 2A, we are given 200 grams of iron. We have to do our molar mass sandwich. So iron, we can just get this one right off of our periodic table. The molar mass is 55.85 grams of iron for 1 mole of iron. Just right off of our periodic table. Now we're going to oxygen. So we look here, there's a 4 in front of the iron. So 4 moles of iron react with 3 moles of oxygen. Now I'm canceling as I go along. And the last thing, oh, I'm not doing oxygen, am I? I'm doing iron oxide. Whoops. So let's erase that. 2 iron oxide. Sometimes I just get going and forget what I'm doing. And we need to know the molar mass of iron oxide. So 1 mole of iron oxide. So let's do that down here. So 2 times 55.85 grams plus 3 times 16 grams. So iron is the 55, oxygen is the 16. Do the multiplication and the addition, and I should get 159.70 grams of iron oxide. So I put this up top. Cancel, cancel. I'm left with grams. So I get 285.9 grams of iron oxide. Remember, multiply the top, divide that by what's on the bottom. And 4 significant digits, because I have 4 here, so I have to have 4 there. All right, for part B, it says, if the actual yield is 252.7 grams, what is the percent yield? So again, percent yield is actual yield over theoretical yield times 100%. I'm running out of lead. Excuse me a minute while I get some more lead. it right. There we go. So my actual from the problem is 252.7 grams. My theoretical from up here is 285.9 grams. Multiply that by 100, and when I do the math, I end up with 88.39%. So now you have enough information to do your homework, which is page 242, number 23. So do that work, and then if you get stuck or to check your answers, the next video will be coming soon. See ya.